Okay, AMA, Accelerated Math Analysis, Section 2.1, Day 2. Okay, so we're going to be looking at really the tangent line slope and the secant line slope to fit real-life motion problems. That's what's going on today. And in fact, today we're going to be looking at something called rectilinear motion. Rectilinear motion means that our motion is in a straight line. Now, later on, as you advance into calculus, you'll deal with motion that could be free to go wherever you'd like. But for right now, let's just assume that we're traveling on a straight line. So here is what's happening. We're going to have a position function S. Okay, S is your position function. And notice that you're going to have time. Your time right here is super, super important. You're going to have a starting time at A, and then you're going to move H units beyond that. So this is like our second definition that we can see. That's your change in time from A to A plus H. You can see it's really just an H. But corresponding to that, we have a starting position, and then we have an ending position. Okay, so you can imagine that we're traveling on the x-axis or the y-axis or any general line. But of course, what you need to take a look at is right here, the average velocity. The average velocity, guys, and you've probably been doing this intuitively for a very long time. You're finding the change in distance over the change in time. That's your average velocity. Now, before we bring this in here, let's just say that your family took a trip and you found out that you covered 100 miles. Your distance changed 100 miles, and you did that in 2 hours. What would your average velocity be? 50 miles per hour. Stating the obvious fact, does that mean every second of your trip you were traveling 50 miles per hour? No way. That's just an average velocity to communicate what was happening on that timing. So again, how do we find that? You need the change in distance. Well, you could say, well, you're ending right here. It's end minus beginning. S of A plus H minus the S of A. That's the change in the distance that you can see. Now, your change in time, you could say, well, if you have a starting time of A plus H time units, ending time of A plus H starting at A, you could see that you've really changed by H. So that right there is your average velocity. So here's the thing. We just mentioned, hey, we know right well, just like when we were traveling 50 miles per hour on a family trip, that doesn't mean that you were traveling 50 miles per hour for every instant. You might say, how in the world could we ever move from an average velocity to an instantaneous velocity? This instantaneous velocity is going to involve the limit. This is going to be a tangent line slope for an instantaneous rate of change, a secant line slope for an average rate of change. And what you can see is we're going to have that second definition. The limit is h goes to 0 of s of a plus h minus s of a all over h. So that's very, very helpful. There very well could be times where you would say, I want to know the velocity at a particular moment, not just over a general time interval. So here's really what we're going to do. We want to be good with our video. We also want to say that velocity is actually a vector. It can be negative, indicating that you're moving in a negative direction. Generally, a negative velocity would indicate that you're traveling to the left. Positive velocity would indicate that you're traveling to the right. But let's jump right in and take a look at an example. We've got a hot air balloon. A hot air balloon on example 2 here. And it says a sandbag is dropped from a hot air balloon that's hovering at a height of 512 feet from the ground. If air resistance is disregarded, the distance is here. Here is your function. So in other words, plug in any t value. Plug in t equals 0, plug in t equals 1, and you're going to be able to get your